Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on MATLAB simulations about control systems theory. Today we are going to simulate higher order sliding mode control with optimal reaching. This control law has been presented in a paper published in IEEE Transactions on Automatic Control. And this is a very nice paper. I recommend that you go to IEEE Explore and download and read this paper. It's a very good paper published in 2009. So this paper starts with introduction section, and then there is a mathematical preliminaries section where the authors provide introduction about what it means for the sliding mode control to be a higher order. So in short, the goal of higher order sliding mode control is to basically attain the manifold where the sliding surface, its first derivative, its second derivative, and its r minus 1 derivative all are 0 at the same time. So before that I have uploaded 2 lectures on sliding mode control where we have basically discussed first order sliding mode control, in which we try to make the sliding surface equal to 0 by using the control law. And once the sliding surface is 0, we have defined the sliding surface in such a way that having sliding surface equal to 0 achieves our control objective. The same concept applies for higher order sliding mode control, but the only difference is that in higher order sliding mode control, you not only make the sliding surface equal to 0, but you also make the derivatives of the sliding surface equal to 0 as well, and these should all be 0 simultaneously. So you define this sigma as a vector, which is a vector of the sliding surface, the first derivative of the sliding surface, and up to so on r minus 1 derivative of the sliding surface. That's the major difference between the higher order sliding mode control and the first order sliding mode control, that we have this sigma is a vector of dimension r for r order sliding mode control. So coming back to the paper, I'm not going to read through the paper because we don't have that kind of time for this video. This is the video about MATLAB simulations, so we'll just look at the main results of this paper, which are presented in this section number 3. And you can see here that the authors have presented, let me scroll down. So this subsection here, they have presented a control law from reference 26, which can be used for second order systems. So this control law v of x1 x2, this is for second order systems where we have only 2 states, x1 and x2, and this control law is equal to minus sine of x1 plus some function beta of v times x2 times the absolute value of x2, and beta v function belongs to the range 1 by 4 to 1 by 2. The authors have also described when is beta close to 1 by 2 and when it reaches, under what condition the beta function reaches 1 by 4. So here beta reaches 1 by 4 when v or nu reaches 0 from the positive side. And then this is a more elaborated form of the control. It is the control function is 0 when x1 x2 belong to the manifold m0. M0 is the manifold where x1 and x2 both are 0, and the control is sine of x2 when you are in the manifold m1, but m1 contains m0, so you don't have to be you should be in the part of m1 which is not in m0. So m1 is the manifold where x1 plus 1/2 x2 times the absolute value of x2 is equal to 0. If this equation is satisfied, then all those points at which this condition is satisfied belong to the manifold m1. And in general, when you are neither in m1 nor in m0, the control will be sine of x1 plus 1/2 x2 times x2 absolute value. So this is the sliding mode control for second order this is the second order sliding mode control, where the control input appears in the second derivative of the sliding surface, and this is also for the second order systems. And this is again another form of the control law. Well, and this is the third order sliding mode control algorithm presented in this paper, and this is the control law for third order sliding mode control. The authors have defined three manifolds. The first manifold is where this is M0 manifold, where sliding surface, its first derivative and its second derivative, all three are simultaneously equal to 0. And then there is second manifold in which this equation and this equation are both satisfied simultaneously. And the third manifold in which this function s of the sliding surface and the first and second derivatives of the sliding surface, this function s is equal to 0. So these are the three manifolds. If the state space belong, if you know sigma is in the manifold M0, then control law u equal to 0 will be applied. And if you are in the manifold M1, which the part of M1 which is not in M0, then control law sine of the second derivative of sliding surface, that will be applied. And similarly in this in the manifold M2, which is the part of M2 in which does not contain any point of M1, you can assume that M2 is the largest manifold, and M1 is contained inside M2, and M0 is contained inside M1. So if you are in that part of M2 which does not belong to M1, then this control law will be applicable. Otherwise this U3 control law will be applicable, which is given by sine of this s function, which is a function of the sliding surface, the derivative of the sliding surface, and the second derivative of the sliding surface. So this is what we are going to simulate in MATLAB today. The simulation example presented in this paper, which is basically this kind of a vehicle which has these two angles, angle theta and angle phi, and these x, y. So this vehicle is moving in a 2D plane with x-axis and y-axis are the axis of the plane in which the vehicle is moving. So these are the equations of motion for the vehicle. And then the authors have defined the sliding surface. The sliding surface is defined in such a way that the vehicle has to follow the trajectory y equal 10 times sine of x divided by 20 plus 5. This is the trajectory that the vehicle has to follow. The sliding surface is defined in such a way that the difference between basically well, if you put this whole thing y minus 10 sine x by 20 minus 5 equal to 0, so that's what is the definition of the sliding surface. If sliding surface is equal to 0, then this control objective is satisfied. So we have the intuition of defining the sliding surface is same for first order, second order, or any order sliding mode control. Here we have third order sliding mode control, but the intuition of the definition of sliding surface is that whenever the sliding surface is 0, your control objective is achieved. In this case, the control objective is to make y equal 10 times sine of x by 20 plus 5. This will make some trajectory on xy plane. So they have calculated the first derivative and the second derivative and even the third derivative of the sliding mode control, although the third derivative is not going to be used in the definition of control law. And then they have presented their control law and control law for two other methods, and then they have compared their proposed control law with the other control laws and have demonstrated the better performance of their proposed control law. We will be recreating these results today using MATLAB, and that will show you how to implement higher order sliding mode control using MATLAB. Right, so let's get started here. I already have the MATLAB open here, but let me just create a new M file, and that's going to be created in a minute. So that's our new M file. Let me just minimize the screen so that you can see with respect to the paper what I am doing. So here, this is our system that we want to simulate. I will open the MATLAB script file editor on the side. So first of all, as I have mentioned in my previous lectures regarding the simulation of feedback control using MATLAB, we have to create a function file here. We make a function dx equals let's call it higher order sliding mode control 1, so HOSMC1. So time and the state vector will be the input to this function, and you can see here that this x dot is our first state. So let me call this dx1. So dx1 is derivative of the first state variable, and that is equal to v times cos phi. So v is some constant here. So if you look at the paper, they have given the value of v is equal to 10 meter per second. So you can define the value of v before you even define dx1. So v equal 10 here, and similarly L is equal to 5. They have shown in the paper, so we define L equal 5 here. So dx1 is cos v times, so v multiply by cos of phi. Phi is our third state variable. So first state variable is x, second state variable is y, third state variable is phi, and the fourth state variable is theta. So I would call it x or x3. So phi is x3 for us, and x is x1 for us. So derivative of x1 is v times cos of phi. We put semicolon at the end of the statement to suppress the output of the statement on the command window, and then dx2 is the derivative of y, which is v times sine of phi. So I'll just write v times sine of x3. Phi for us is x3. Similarly, the third derivative phi dot is dx3 for us, and that is equal to v divided by L times tangent of theta, which is x4 for our case. So theta is our fourth state variable. So we have defined, and finally dx4 is equal to, so theta dot is equal to u, so dx4 is equal to u in our case. So now, and finally dx, which is the full state vector, that is equal to actually dx is the derivative of the state vector, x is the state vector, x is x1 x2 x3 x4 for us, and so dx will be dx1, dx2, dx3 and dx4. So this is how you can write the function, but it's not complete yet because we have not defined what is the u here. So u will be our sliding mode control, which is given here. So this is the control law that the authors have proposed. This is the optimum what do you call it, the the higher order sliding mode control with optimal reaching. So this is higher order sliding mode control with optimal reaching, and OR. So you can see subscript OR is for optimal reaching. Alright, so this control law we have to define. We need the value of alpha. Value of alpha is given somewhere here. So alpha is considered a physical constraint. So the authors have told us that they have selected the alpha to be equal to 20. So we go back to this file and we define alpha to be equal to a in our file, a equal 20. That means alpha equal 20, and then we have to define the u is equal to, you can see here, I just push it a little bit on the side, and this one gives me so this is the control law that I am going to write in the MATLAB code. So this is equal to minus alpha, which is a in our code, times sine. So sine function in MATLAB is sign, sine of so this whole thing in the brackets. So first of all, there is a sliding surface involved in the paper. So let me just minimize this and make it a little bit larger, maybe 150 degree, 150. So this is our sliding surface that the authors have defined in their paper. The sliding surface sigma, we call it S in our code. S is equal to y. So y in our case is second state variable, which is x2. So x2 minus 10 times sine of this is x in our case is x1, that's our state variable in the code, divided by 20 and minus 5. That is our sliding surface that is defined in the paper. And the next is the derivatives of the sliding surface that are going to be used in the control law. So we are going to use these derivatives of the sliding surface. So s dot, that is equal to, so we call s dot equal sd in our code. So sd is equal to v we have already defined to be equal to 10 in our code. So v times this sine of phi, which is in our case x3, and then minus 1 by 2, which is 0.5, times cos of 0.5. So let me just give some space here to clarify, to make the code clearly visible. So minus 0.5 times cos of x is x1, so x1 by 20. And then once you complete this code, multiply by sine of phi, which is basically x3, and then you close this bracket. Okay, I made a mistake. This is not a sine, this is a cosine. So let's just check here that sigma dot is v times sine of phi, which is sine of x3, minus 0.5 times cos of x1 by 20 times cos of x3. So that's our sliding, the first derivative of the sliding surface. Similarly, we can write down the second derivative of the sliding surface. So second derivative of sliding surface, we call it SDD in our code, and we write it as this is v square v square divided by L multiply by, so there is tangent of theta is x4 in our case, and multiply by cos of phi, which is basically x3 in our case, plus 1 by 2, which is 0.5, times cos of x by 20, which is x1 by 20 for us, and multiply by sine of phi, which is sine of x3 for our case. And now we close this bracket where we have the tangent one, and then we add plus L by 40 multiply by sine of x by 20, which is x1. So you have to be very careful while writing these codes, because you can make you can easily make some typos or errors. So x1 by 20 is sine of x1 by 20 times cos of x3 whole square, and then we close the bracket off. So this bracket is the multiplication with the, so this is our the second derivative of the sliding surface, which is v square by L tangent of theta multiplied by we have to double check that cosine of phi plus 0.5 times cosine of x by 20 into sine of phi plus L by 40 into sine of x by 1 by 20 into cosine square of phi. That's all. So we have defined the first and second derivative of sliding mode control. So we can come back to, so here you can see that this is the control law that we are trying to write here. So minus a times sine of the sliding surface, now we have already defined it, so it is s plus the cube of the, so s dd raised to the power 3 divided by 3 times a alpha r square. So we don't know the value of alpha r yet, so we look into the paper and there should be a value. So let me just maximize it. So there should be a value of alpha r given in the paper. So here it is. So alpha r is equal to alpha km minus c, and this is equal to 10 in the paper. So we write alpha r equal 10. So we represent alpha r by ar equal 10. This is given in the paper, so we use the value that is provided in the paper, and we go back to this control law. Okay, so far we have the control law minus alpha times sine of sliding surface plus std cube divided by 3 ar square, and now we move on plus u2 divided by square root of ar and multiplied by, so I will define u2 in a minute, because u2 is something that has been, so this is u2 multiply by the derivative of the sliding surface is SD plus SDD SDD square divided by 2 times alpha r 2 times AR, and that will be raised to the power 3 by 2, so that's 3 by 2, which is 1.5. so this raised to the power is with this whole thing. So you can see here that this whole thing is in the bracket, and it's raised to the power 3 by 2 in the code as it is in this equation. So after that we add plus u2 multiply by SDD, which is single derivative SD multiply by SDD and divided by alpha r. That completes the equation for our controller, but we still have to define u2. So since u2 is being used in the equation of u, we have to define u2 before we define u. So u2 is equal to, you can see here, u2 is equal to sine of SD plus SDD multiply by absolute value. So absolute value, the function for absolute value in MATLAB is ABS SDD and divided by 2 times alpha r, and that completes so this is the equation for u2, which is sine of the first derivative of sliding surface plus second derivative of sliding surface times the absolute value of the second derivative divided by 2AR, and then u is equal to alpha times sine of, so let me just check, yes, it looks okay, but let me just double check this. So UOR is sliding surface plus this cube over 3 times a alpha r square plus u2 divided by square root of AR multiplied by u2 plus SDD square divided by 2 alpha r raised to the power 3 by 2, and then plus u2 into SD times SDD divided by alpha r. So that looks okay. We will see. So let's save this file. So this will be saved by the name of higher order SMC1. We save this, and then we create a new script file and CLC clear all, close all. These are just standard commands just to make sure that any previously opened figures or any previously defined variables do not interact with our code. So I give the command t comma x equals ODE 45 and at the rate higher order sliding mode control 1, run it for 0 to 20 seconds. Actually this is given in this paper. They have run the simulation for about 20 seconds, so we are going to do. Alright, so we have the initial values of the state variables. We can use the same values that have been used by the authors. Those are all zeros, and then you can this command is complete. Now we need to find plot the trajectory. So you can see here that in this paper they have plotted x versus y. So you can see here in this graph that they have plotted the y versus x. So for us, basically, if I plot, x is our the state, x is the first state variable, so x is the x all rows first column, so that is the first state variable versus the second state variable, which is y. So we plot it like this, and we make like grid on, and maybe we can add x label to be x and y label to be y. And now we can just run this file and see what happens. So we are going to save this file with the name HOSMC underscore script, because that's easy to remember what is the purpose of this file. So I have run this file, and let's see what comes up. We have to wait a little bit, maybe, you see the MATLAB is busy. The differential equations are actually quite heavy, so it's going to take some time to simulate them. There's going to be a lot of computations involved. We are still waiting for the solution, and still waiting. It might take about 30 to 40 seconds because these differential equations are going to be solved numerically, and sometimes the step size is really small, and the step size for solving the differential equation is chosen by the MATLAB itself. If you are familiar with the numerical analysis method, ODE45 uses the RK method of order 4, if I remember correctly. And alright, so finally the results have arrived, and this is the result of our simulations. And now let us compare these results that we have obtained with the results in the paper. So these are the results in the paper. You can see here that this is our trajectory, and this black trajectory is basically what we have replicated in our simulations, in our code. So this, you can see that this varies from -5 to 5, and the same is here in our case, -5 to 15, and the peak value is 15, and the lowest value is -5. And now that we have simulated the optimal controller, let us also add these curves into our plot. So for example, this is the ideal reference trajectory which is being tracked, which is supposed to be tracked, and this is the trajectory due to other controllers. So let us try to simulate those as well. So far we have written this code. So we have written the function file for our sliding mode controller, the third order sliding mode controller, and we have written a file which calls that function file and generates the results. And now we are going to write so let's see. So in order to write the code for the other controller, so let me show you the other controller. So this is the so far we have written the code for this controller, optimal controller. Okay, so now let us let us simulate this controller as well. So UL, so for that what we need to do is we can just copy this, select all of this code that we have written for this optimal controller, control C, create a new file, and control V, paste it, and change the file name, the function name here, and make it HOSMC2 and save it as a separate file, higher order SMC2. And what we are going to do here is that we are going to, only thing we are going to change here is the expression for the controller U. So what I'm going to do is, we don't need U2 in this case, and the expression for U will be the new one. So what I'm going to do is I'm going to remove this existing line for U, and now you can see here that this UL is a minus alpha, which is A in our code, times sine of SDD plus beta 2. So beta 2, so you can see here that there are two new parameters, beta 1 and beta 2, that are used in this controller. So here we can search for their value. So here beta 1 is 1 and beta 2 is 2 in the paper. So we say b1 equal 1 and b2 equal 2. The values are given by the authors in the paper. So we go up in the controller equation and we see that this is double dot plus b2 times this absolute value of SD whole cube and plus S square, and this all raised to the power 1 by 6. So this is 1 by 6, and this is multiplied by sine of SD plus B1 times absolute value of S raised to the power 2 by 3, and then multiplied by sine of S, which is the sliding surface. So this closes the bracket, and this is, wait, what bracket is this, and this is the extra bracket, so remove that, and let's just double check the controller. It's minus A times sine of double derivative of the sliding surface plus beta 2 times absolute value of the derivative of sliding surface to the cube plus sliding surface square whole raised to the power 1 by 6 multiplied by sine of the derivative of sliding surface plus beta 1 times absolute value of sliding surface raised to the power 2 by 3 multiplied by sine of sliding surface. That looks correct to me. Hopefully there are no mistakes. So what I have done is I have just changed the expression for the control input. Everything else is the same. I save this file, and now in order to compare this in the script file, what I do is I copy this file, this command, control C, control V, and I just want to rename these values T1 X1, and this here I'm going to call the other file HOSMC2, And okay, so what is going on here is that I will solve this differential equation HOSMC1 and get the trajectories into t comma x, and then I will solve these the other differential equation with this other controller and solve the trajectories and store them into t1 comma x1, and then I can basically use the command hold on. I can use the command hold on after this label command hold on, and I can plot the same x1 x2 control C control V, but this is the other trajectory. So these are the so x1, this name comes from this x1, so this comes from the other trajectory, and I also want to use different color for this, so I would just use dotted red lines for this plot so that I can see the difference. And then what else I can do, if I look back into this research paper, I have this they have also plotted this reference trajectory as well. So if I want to also compare the reference trajectory, I don't have to solve any differential equation. What I will do is, you can see here that the x values are almost 180 or 200, 0 to 180. So what I will do is I will define another variable, say x2 equal 0 to 0.1 up to so on 180. This will be a vector, and y2 will be equal to 10 times sine of x2 divided by 20, which was actually the equation for the sliding surface, because sliding surface is selected based on the control objective, and our control objective is to follow the trajectory where y is equal to 10 times sine of x divided by 20 plus 5. And now we can also plot control C, control V. Notice that this hold on command will hold the figure, and all of these plots will be sketched on the same figure. So here I can use dot dash and green color, and I don't need this vector notation. This is x2 and y2 are y2 and x2. These are scalars, these are vectors but not matrices, so I can plot these vectors. x2 comma y2, this will plot the xy relationship that depicts this curve, this ideal trajectory. And now in my MATLAB code, I have I get the trajectories for solving the optimal control based differential equations, the Levant control based differential equation, and then I plot them here. This is the plot for optimal trajectory, this is the plot for Levant control based trajectory, and this is the plot of desirable trajectory. So we can run this file and get the results. This file is calling this function and the other function, the optimal control function. So let me just run this file and we shall see how the result turn up. Alright, so finally the results are here. Let us look at the results. So here you can see that the green line shows the ideal trajectory. Let me pull out. So this is the what have been published in the paper, and this is what we have generated using our MATLAB code. You can see that side by side, that this is the green line shows the ideal trajectory, and here this dash dot line shows the ideal trajectory starts with 5 value, and then this blue line here shows the trajectory that we plotted using the optimal control, and this is the trajectory that results from the Levant control, the Levant third order sliding mode control. Alright, so here you can see there is some slight difference at the beginning, our control and the control in the paper, and let me show you where this difference comes from. So here if you look at the paper, they say here, so they say that the simulations have been carried out in time horizon 0 to 20 seconds, which we have also done the same. The controllers have been enabled only at t is equal to 0.5 seconds. They have their reason for doing that, but what they have done is they have enabled the controller at t is equal to 0.5 seconds, and so what we can do the same here. So what we can do is we go back to our code file here, and just before the line where we define the control input u, we say if t is greater than or equal to 5, then you press a tab button just to make the alignment correct, and then else u is equal to 0, and so with that you can just get it back here. Okay, so this if command will ensure that okay, not 5 but 0.5. so this command will ensure that when time is greater than 0.5 second, the u will come into play. Otherwise when for the first 0.5 seconds the u will be 0. So you can do that here also. Before I run the revised trajectory, I also want to show you something. So here is the theoretical result. This is the proposed third order optimal convergence or optimal control. So this is third order, I keep on forgetting its name. This is optimal reaching control. So the third order optimal reaching control is given by this equation. So in the case study you can see the control is, there is only single control here, UOR3, there is just one equation, whereas in the theoretical result it is basically a switched control where under certain condition control is 0, under some other conditions control is this, under some other conditions control is U2, and in so we have only used this controller. So if you compare this U3, what we have used in the simulations is only U3. So but the authors have justified this, stated this already in the paper, that switching surface is a zero Meyer set. It is sufficient to use the outer switching surface when implementing the equation 12. So this is equation 12. So they have said that for this particular case study it is okay just to use this outer surface and ignore, you don't have to use these surfaces. But I want to show you that if we had to use, if we had to implement this control u as it is, as equation 12, then how would we do that? So for that what you do is you implement the control for 4 different cases. So for example, so what is m naught? M naught is when s dot s triple dot all are equal to 0. So we call this condition 1. So this is our code for the optimal control. So here what we do is we define condition 1 C1. This is equal to a logical statement s equal 0. This is a logical statement, it will be 1 if s is equal to 0 and 0 otherwise if s is non-zero. So and this is logical AND operator, sd equal 0 and sdd equal 0. So it's very important that you put parentheses around the conditions so that the MATLAB knows that there are 3 separate conditions and there is AND operator. So this is condition C1, which shows that which will be C1 will be equal to 1 if all of these 3 are equal to 0, otherwise C1 will be 0. So this basically will C1 will tell us whether we are in M0 or not. So and similarly we go back to the code and we can just implement the condition 2 C2, which is basically this condition, which is the condition relevant to M1, and the condition relevant to M1 is that so the first condition is s minus sdd whole cube divided by 6 times ar square. So this is equal to 0. So we have to put double, so this logical operator. So this is the first condition that we have here. Let me see if I have I think I have an extra parenthesis here. So this is the condition. Let me see. So sigma minus sigma double dot cube divided by this equals 0. I think I've got it right. So this condition and this other condition, which is sigma dot sd plus sdd multiply by absolute value of sdd and divided by 2 times alpha r. This has to be equal to 0. So this is the second condition, sd plus s double dot multiplied by the absolute value of s double dot divided by 2 alpha r. So this will be double equal sign, equal 0. So this is condition 2. So how can I implement the control? Well, what I can do is, so if C1 equal 1, which means that sigma belongs to manifold M0, then u is equal to 0, else if so C2 is equal 1. So else if C2 equal 1 means that C1 is not 1. So we have M1 satisfied but not M0. So then in that case u will be equal to sine of sigma double dot. So that will be sdd. Alright, so this is sine of sdd, and here you can see that we have if condition C1 is satisfied, then u0 is we use the control u0, which is 0, and if condition C2 is satisfied, then we use the control U1. And if condition, so we have to define another condition, condition 3, which is that sigma belongs to M2 and not belongs to M1 or M0. So we have to use here else if C3 is equal 1. So then the control U will be equal to U2, and we have already defined this U2 up here in the code, so we don't have to redefine it, but we do have to define our condition C3. So condition C3 is simply this function s here. So you can see that M2 is s equals 0. So whenever this whole function s is equal to 0, then condition C3 will be satisfied. Luckily we have already written down s in the code in the expression for u. So what we do is we control C, copy this value of s from the expression of u that we wrote before, and we press enter here, and we say C3 is equal to that this s equal 0. So whenever s is equal to 0, C3 will be satisfied, and whenever C3 is satisfied, then u will be equal to u2, else u will be this sign. So this is, and then we have to end this if statement, else all these conditions are set done. So we press and enter here and write down end. So this is, so notice that this else if all these conditions are representing the corresponding conditions in the paper here. So I have translated the manifold conditions in the paper in terms of this C1, C2, C3, and I've added them here. And now, and the other condition is also there, that we apply the controller for t greater than equal to 0.5. Whenever time is less than 0.5, the controller is 0. So we save this file and we go back to here. So we don't change the Levant controller, and we come here, and here I want to add another command, legend. So legend command, what this command will do is, actually it will add this kind of thing. So you can see here in this figure, this box representing which signal is which. You can add a legend here. So we have 3 signals plotted in our code, so we have 3 legends. So first we have plotted this here we have plotted x and y states for the optimal OR controller. So here the first legend will be OR, and then secondly we plotted this x1 state variables which come from the Levant controller. So we plot here, we say the second legend is L, like this. And then the third legend is that we have plotted the reference trajectory. So reference shall be the third legend, and then we can run this file. And once you run this file, I've already done this before in the background, so I can just show you the results. So here are the results. When you run the file, the results will look like this. So you can see here green line here, this green line, this is reference, and this red line is the Levant controller, and this blue line is the OR controller. And now you can compare this initial value are the same because we start the controller at 0.5 seconds. So this was it. We can also plot the other results here, sigma, sigma dot, and sigma double dot. We can plot by adding the code here. So this equation of sigma so here we have this equation of sigma. I'll just do sigma, and then you can do sigma dot on your own. I'll say the control C and paste this in the script. So for example, here I want this, but this sigma is going to be a whole vector, x all columns, comma 2, minus sign of x all columns comma 1, and that will be x. And I want to plot so I will add figure 2 and just plot the t comma s. I can do that. So I don't have to, for right now I don't have to rerun the file because the trajectories have already been computed. I copy this file code, control C, and paste this into the command window and press enter, and you can see here the sigma is plotted. Let's compare this with the this plot here. You can see that the sigma goes to around minus 8.5, which is the case here. This goes to around minus 8.5 and then it settles to 0 at about 3 seconds, and here also it settles to 0 at about 3 seconds. So if you want this plot to be exactly the same, we can do that as well. We can say the y-axis in this plot is minus 15 to 5 and x-axis is, so we can put the axis command. The axis command will make the axis so x-axis is 0 to 20 and y-axis is minus 15 to 5. If I press enter, let me see if the axes have been adjusted. You can see here now the axes have also been adjusted, minus 15 to 5 and 0 to 20, and now you can compare this. The plot remains the same, so there is no difference in the plot. Just it is just, you know. So that's how you can recreate the results in a research paper. And so today's so let me show you the final code that we have written in the lecture. So let me maximize this. So we have written 3 files today. This is the first file that we wrote. This is the function, the third order sliding mode control with optimal reaching, and we added some conditions into this control as well. And this was the second file that was basically a copy from the first file, except that this control law is different. This is the Levant third order sliding mode control, and then we wrote this file which calls these functions. And you can see once you call the ODE45 function, I can show you the size of the x. So size of x, you can see here that x has like around about 2 million, so more than 2 million data points in x and 4 columns. So this means that these are 4 state variables, and they in 0 to 20 seconds there have been more than 2 million data points. That's why it takes so long to run this file. But you can also set the step size as you want. Like here, if I tell the MATLAB that 0 to 0.01 to 20, then my step size will be 0.01. So I can tell the MATLAB to a larger step size if I want the code to run quicker. And this is the paper once again that we have formulated, we have simulated. So this is the this is the case study example that we have simulated, a car example, and this was the third order sliding mode control with optimal reaching that we have simulated. We have also compared it with another control, Levant. Hope that this lecture was useful for you. If you have any comments, please let me know. Thank you for watching this video.